So, good morning, good morning. Today is September 28th, and we don't need the glare of my hallway there. We had some questions we thought we'd address over the Unit 1 review and or the Unit 1 project, and then we're going to move on to lesson 2.1 today. So number 8 was the question on page 108 of the Unit 1 review. It says a model of the Space Shuttle Challenger has a scale of 1 inch for every 64 feet. The actual shuttle was 122 feet in length. How long is the model? So let's go to share my screen here. Does anybody have an idea on this one before I give my 2 cents?
I kind of just made like a weird guesstimate, kind of.
Mm-hmm.
How did I do this? Okay, so I first did like, I don't know, 64 plus 64 to get 128 feet
Mm-hmm.
to know that, so we can have 1 inch. And then I just like kept adding smaller numbers until I got 122 exactly plus 64. So like a number plus 64.
Mm-hmm.
And then so I got 64 plus 58 equals 122. And then this is probably totally wrong, but I divided 58 by 64 to get like, I rounded up to 0.91.
Mm-hmm.
And so I did 1.91 inches for my answer.
Okay. Without writing it down, it sounds like it might work. I'm going to go through mine and we'll see if we come up with the right same answer.
Okay.
Okay, no, I like that. I love when students come up with different strategies and ways to do it. So how I would, and we all think of this different, as I would think of this as 1 inch is compared to 64 feet. And this is the model, right? These models in real life get a little bit tricky because they're both in the same, they're both in length. And so it's kind of hard to keep them the same, separated. So if I want to equivalate this, get this to an equivalent of 122 feet, the actual. So this is the model, right? So a model says that has a scale of 1 inch to 64 feet. So that means 1 inch on the model is 64 feet in real life. But they said the actual shuttle is really 122 feet. So I have to figure out then how big was the model. And so one way we could do is I could say, how many times bigger is 122 times bigger is it compared to the 64 in the model? So 122 divided by 64. And I could share my Desmos. So in Desmos,
1.906.
Awesome. So 122 divided by 64. So we got 1.906. So that means it looks like Stephen's strategy was right. So that means I can take 1.906 and I should be able to multiply that by my 1 on my inches. And actually, this is an interest. Oh, no. Sorry about that. I bumped something in my share. That we're going to cover in actually lesson 2.3 more formally. So that's why there's different ways you can do this. So I can take my 1.906, and if I'm going to multiply by the equivalent of 1.906 and 1.906, because if that's what I multiply by to get to this, then I have to multiply by an equivalent one fraction. So this is going to be 1.906 on the model. Great job. So that one's a little bit trickier because we didn't really spend a lot of time on that in this unit on equivalence and building up. Good one. Any other questions on the unit one review that anybody has? Also, I really recommend on these really big numbers that you use Desmos. Don't try to do things by hand. Desmos is your friend. What about the unit one project? If everybody needs, a day or so to, keep working on the project, I'm happy to allow you to do that. If you have questions, I probably won't even start looking at the projects till this weekend sometime with the unit one reviews. So,
I have a question on the review on 6C.
sure. 6C. What was your question, hon?
I didn't know how to like set it up.
So it says write a conversion. Let's go back up here where it's saying write a conversion factor relating Bitcoin to USD. So we could go either direction, right? But one Bitcoin is the same as $10,167.10. USD is in dollars. And then the euro compared to Bitcoin, we're going to do another one over here. Then in B, it was asking you to do 32,000 US money into Bitcoins. So you had to do some US dollars to Bitcoins, right? But then in C, you're going to have to do a double conversion. Did anybody get through this one?
I did. I think I might have gotten it right.
Okay, what was your strategy?
I did 1,200 euro into Bitcoin, which is 0.132 Bitcoin, and then I did that 1.32 times the 10,167, and then I got 1,200 euros is a 1,342 USD with 5 cents.
Okay, so do you see, Carter, where we don't have a direct link from euro to USDs up here? So kind of like what we did in earlier in unit one, we had to do multiple, unit conversions. So we're going to have to do a euro to Bitcoin because we do have that exchange up here. The 1 euro is equivalent to 0.00011 Bitcoin. So we'll have to use that in some fashion to translate euros into Bitcoins. And you might end up using the flip. Remember how they can be used in either way. And then you're going to use that to get into the dollars. Does that help you get started?
Sort of, I guess.
So let's first go from euros to Bitcoins. Do you see the strategy where we don't have a direct link from euros to dollars?
Yeah.
Okay, so we have euros. So if I can get to Bitcoin, right? If I can get my euros to Bitcoin, I do have a link from Bitcoin to dollars. Would you agree on that?
Mm-hmm.
Okay, so what can I do with my 1,200 euros to get to Bitcoin? Using my,
Is it over the 0.0011?
so if I do that, if I take this right here and I multiply by that, am I going to cancel out my euros?
I'm not sure.
Well, let's go back. That's where I want to make sure everybody's using their workbook as a reference. So if we go back to unit one, I think it was lesson 1.4. So back to unit 1.4, we had to do some canceling of units, right? So at the beginning, we said, if we wanted to change our milliliters into liters, then the milliliters, to cancel those out, the exchange had to be on the, if it was in the numerator to start, it had to be in the denominator to cancel out.
Mm-hmm.
Because we said if we use the milliliters in the numerator, then we were going to multiply straight across and get milliliters squared over liters, but then we would have 2 units and we didn't want that. So if I do that here, if I do the €1 on top and the 0.0011 Bitcoin on bottom, will my euros cancel out?
No.
No, because I'm going to get euros squared, right? And I'm going to get Bitcoin, and I don't want both of those. I want them to be flip-flopped. Right? So that my euros cancel.
Yeah.
And then we'll be all in Bitcoin, right?
Yeah.
And then I can do the same with using this fraction up here, either this way or the other way, right? I can write it both ways. And I can do the same.
Okay.
So I'll let you work on that for a minute and see what you get, and then we can go back to it if we need to. Does anybody else have another question on the review that they wanted to go over? And we'll let Carter work on that. for a minute.
Not really a question, but I've been kind of having a problem with the scientific notations only because at my old school, we never really did them.
Mhm.
So I didn't have to take a 4th-year math credit because of doing Career Center.
Oh.
So
Mhm.
I really don't like, I mean, it's not like the hardest thing in the world, but I know it's just moving over the decimal. But I've never really learned a good way how to do it.
So, like a number 9.
Yeah.
So a number 9, I would just put these into Desmos.
Okay.
So
I've never used it on my laptop.
Desmos.
Yeah.
You'll want to get fancy with it because we're getting fancy with it in unit 2, and we're going to use it in unit 2 and 3. Sometimes you'll have to turn in a link to me to show me your work. So it'll be
Okay.
important that everybody starts using that. So this is a good step for us to use this. So it says calculate the actual difference. So in 1971, this was our national debt. And then in 2014, this was our national debt, right?
Mhm.
So if I wanted to find out the actual difference, what would I do without worrying about the numbers being big and in scientific notation? What would I do to find the actual difference?
Just subtract one from the other.
So which one am I going to subtract from which? Because it could matter, right?
I was gonna say the bigger one, just because, well, positive numbers are good numbers.
Positive numbers are good numbers, but we actually have to do the newest, the 2014 subtracting the 1971, because you're always going to want to compare the new to the old.
Okay.
And then you can type that in scientific notation. So I'll kind of get you started on that. And then I'm going to go back and make sure Carter, see if whatever help he needs extra on his. We'll go back and reference that. Oh, what am I sharing? Am I sharing my Desmos screen?
Yes.
Okay, so here, if we're taking the 2014 number, I'll type this one in and and I put it in parentheses, so my whole scientific number gets kept together. 782 4071 380 73382. I think I typed it correctly. Times 10. And then to do an exponent in Desmos, you do shift in your 6 key. We'll put it up in the exponent and then 13. And then it's telling you that you need to have a right parenthesis to close it out. And then you're going to subtract, right? And then you're going to type your other one in parentheses. So I do everything in scientific notation in Desmos.
Okay.
That should get you started.
Okay.
And Carter, did you get a little bit further on your other one? Do we need to go back to that and check it?
Yeah, I got
You what?
1,342 for the USD.
So you got, is that what Brandon had? I don't have mine done yet.
I got $1,342.05.
Is that what you said, Carter? It sounded.
Yeah.
It sounded
Yeah.
similar. It was?
Yeah. Yep.
Oh, Carter's breaking up. I didn't quite hear you.
Yeah, I think we got the same answers.
You got the same thing then?
Yep.
Awesome. So that helps us there. And then
I also had another question.
uh-huh.
It was on number 10. I guess I just didn't know how to like do it.
Okay, so what was your setback there on number 10? So for 1.7,
Yeah. Are we like supposed to make it look like problem 12?
no, you don't need to make it as big as problem number 12, because this just says Michigan's House of Representatives has 110 seats. In 2017, Michigan had a population of this. When the 110 district maps are drawn, how many people must be in each district for a proper apportionment? So I'm just saying, what would my standard divisor be, basically? So if I were to evenly spread it out, what would it be? And then you're gonna use a whole number. And then remember, what we can't get part of a person, right? So that's why we do some kind of a whole number. And then number 12 is when you're taking this a little bit step further and you're like, oh, well, I have to divvy these 110 seats up. But you don't have to go that far. So I'm just asking you to figure out what would my standard divisor be if I were going to divide these up.
Okay.
Yep, on that one. And then 11 is kind of building on that. We've got between 77,000 and 91,000 are represented. And so it says calculate the relative error. So, and using the estimated maximum. So we're using the 91,000 here for folks that were not sure on that one. That was a question before in a past semester. Then number 12 is a bigger one, like the 1.7 worksheet. But we're only asking you to Hamilton's here. You don't have to go through Jefferson's and the Webster's. Any other questions?
Yeah, I just entered all that stuff in Desmos and it didn't pull up with any
Did it?
kind of answer. No, I put in the parenthesis and then the first one, and then minus end parenthesis, and then minus the other one in parentheses, and it didn't pull up with anything.
It didn't give you an answer?
No, I don't think I typed it in wrong. I think I just copied what you did on the first one.
So you have what I have here minus, and then your other number right here.
Yeah.
So 3.98.
Yeah, like see, right there where yours has the equals 1.7824. Mine doesn't have anything like that.
So you must have an error over here. Does it give you a triangle with an error? So if you click on that, it'll tell you what's wrong.
No, it didn't. It's blue.
And you hit enter? Well, you don't even have to hit enter.
Yeah, I clicked enter and it just sent me down to like the next part.
Can you share your screen?
Yeah,
Just
one
on
second.
Yeah, if you can share your screen, let me stop sharing mine, then we can kind of see what's going on with that.
I don't know if you can see it or not.
Let's see, for some reason over on the left. Okay, now you're there. Oh, because you're using X. So you need to use a symbol for multiplication,
But okay.
a math symbol. So either the asterisk in the number keypad or the asterisk above your 8.
Oh, okay.
So it has to know that you're multiplying. Yeah, you have to use symbols so it knows. It's
Okay.
it's using a times because that's a symbol it uses for scientific notation.
Okay.
Yeah.
Uh,
And also on yours, you flip them around again. You put 3.98 first, and that's actually the 1971, right?
yeah, that's what you said. You said do the old by the new.
No, I said the new minus the old.
Oh,
So you
well,
want,
it should be the same answer, just one's negative, one's positive.
right, but that would make a difference though on your number, right? Because we didn't go down in spending, we definitely went up in
Yeah.
spending.
Okay.
Yeah, good job, great
Thank
question.
you.
Any other questions? Great questions. This is fabulous. So I'm going to be getting, putting up the Unit 2 project. I'm modifying it a little bit from what the lead instructor had up there. So it's going to have 2 parts. And we'll kind of maybe spend some time on the project on Thursday. Because, well, actually, let's just spend a few minutes on it right now. I think I have it up. I do. So am I still, I'm not sharing my screen. Let me share my screen here. And I promise we'll still get through 2-1. Shouldn't be a problem. Okay. Can everybody see my screen? So this is essentially Unit 2 project. There's 2 parts to it, 2 tasks. I'm asking you to pick a stack, and you're going to go to either of these links here. So you can also go by searching stacks.
Quick question.
Uh-huh.
Can I just pick a stock that I'm invested in right now?
Yeah, you can pick any stock you want. I'm just showing how to get there.
Oh, okay.
So you can go stock prices if you want and type stock prices today to help you get started following a stack. But any of the ones that we had suggested here, it says a finance.yahoo that came up on mine or www.nasdaq. So any of those links. So you can see the finance Yahoo, that one came up. So if I go there and I choose a stock that I want to follow, let's see. So we're going to go to, I'm going to click on the finance home right here. And you can click on S&P is one area that you can, there's certain countries that are in this grouping. There's certain in the Dow and there's certain in the NASDAQ. So you could go to S&P 500 and search what stocks if you want. Now, actually, I think if we just search a company up here, that might be easier. So let's say I wanted to invest in Disney. Disney's having their, I think, 50th or 100th anniversary. So if I want to invest in Disney, I'm going to click on Disney and it's going to give me their symbol. And I'm just going to click on DIS for Disney. And it's giving me lots of information. Now, don't get too worried about this information here because we're going to do this in Unit 3, but I just want you to be tracking their prices. So every day, so you're going to track the price. So here's the current price. And notice it's changing by the second. So you can either do the previous close and start there or the opening bid. So if you do on the open, see where I'm grabbing this right here. So today I could mark for Disney. Every day I'm going to track and I'm going to use this open. So I'm using a consistent opening value. So I'm going to say today's was 176.63 cents. So let me go back to the project. So I want you to pick a stack. You're going to record the opening value of the stack every day for 2 weeks. Okay, so you could make a table or you could make a table in Excel if you wanted to. Okay, so if you wanted to do an Excel spreadsheet, you could do that. You could make a column that says day 1, day 2, day 3, and so forth. Okay, so you're gonna do 2 weeks worth. Now, remember, well, you probably don't know this, so it's not remember, but I want to tell you that in stocks, they only do Monday through Friday. So you're only going to have 10 days because that would be 2 weeks in the stock market. So my Disney then would be, what I say, 176.63 or something like that. So I'm going to track these. So we're going to essentially use this information here in Desmos. So then it says create a table containing the date and the opening value. So what I'm going to do is I'm going to suggest that everybody uses Desmos. So then you can keep track of everything right in here. Oopsie. And I actually think that I have one. Oh, whoops. I'm not even logged in. How am I not logged in? Let's see. I don't even know what my login is. Okay, so here I am. So I believe I have one from unit 2. Let's see, unit 2 project test 1. Let's see. So here it is. So I will send you all this link here. And I'm going to delete that. So I will send, put all this link in where I post the project, and you're going to create you're going to write what your stock is. Notice where see where it has quotes over here on the left, that those are notes where you can just type in word answers. And then anytime you want to do a number, you're going to just go to where you want to enter it. So it says enter your data into a table. So I'm going to go up to the plus and hit make a table, and then it will make a table below there. Okay. And then throughout this, the next couple lessons, we're going to learn how to find the equation and the correlation. Don't worry, we're going to walk you through all of this. So this will this will get you started. So that's for project test 1. So I'll put that link up in Desmos. I'm sorry, in JetNet with this description right here. And then you're going to read through and you're going to finish these other answers here. But they're going to be in Desmos. So you'll answer it right in my Desmos. Then the other task is finding some kind of a recipe online, or your mom's favorite recipe if you want, or something, or your favorite grandma recipe. And you're going to find out how many people the recipe is written to serve. So if it says number of servings is for 8 people, then that will get you started. Then you're going to do the scaling. We're going to do scaling in lesson 2-3. And the scaling, you're going to use your scaling to rewrite the recipe to serve 1 person, and then you're going to rewrite the recipe to serve 100 people, 100 servings. So you're going to scale down and you're going to scale up. And like I said, we're going to do that in lesson 2-3. But this will get you started for those that want are interested in learning more about the project. Does that help everybody there? Kind of get you in the thinking of the project here? I'm going to save that. And I'm going to go to I want to get a new. Anybody have any questions so far? Ready to start 2-1?
I just have a question where we turn in our unit 1 project. Try to click on the unit 1 thing that says due September 30th, and it just takes me to the download.
Oh. Yeah, that's what you're gonna, it takes you to the download, which should be where you attach your project. Let's see here. Right here. Oh, I'm not sharing my screen. That would be helpful. Right here, Stephen.
Hold on. Oh, just kidding.
Oh,
I was trying to click on the one above, that's why.
that's okay. I just want to make sure I was showing that correctly. Okay. So let's go ahead and start lesson 2-1. And I will give more help along the way. And to be honest, I think the other projects, so if you're feeling, which I don't blame you because I'm not enjoying Unit 1 project either, it's quirky. I think the Unit 2, 3, and 4 projects are much easier to manage because you don't have to learn as, we're already using Desmos, and so most students, it actually helps them more than it does distract with the whole Excel thing. So Unit 2, we are contending with change. So today we are starting on page 125. And the title of this lesson is Avoiding Empty Pockets. And you can read through here if you'd like. And we are going to start down at the bottom, discussing any experiences you've had with important financial situations. So has anybody here had to manage a credit card or a checking account, borrowing money to buy a home or a car? Probably not yet, maybe a home, but maybe a car.
I didn't have to borrow any money. I just paid for my car with cash.
From savings?
Yeah,
Wow, good for you.
thank you. I worked a lot over the summer and I didn't spend very much.
Wow, that is awesome. Good for you.
Thank you.
I had to do loans just because I didn't make that much when I was working in the summers. Anybody else have any experience or know any understanding on like savings accounts or retirement accounts? We're going to learn about a lot of this really in Unit 3, but we're going to be introduced to it today because we have a necessity. So interest is a fee paid for the use of someone else's money. So if you borrow money to buy a car, you're going to pay the bank or the lending institution or your parents possibly money to borrow money to buy that car. And if you put money into a savings account, then that means the bank is going to pay you. Usually it's very, very small amount of interest, but they're going to pay you to use your money in that savings account so that they can use that money and invest in other things. So sometimes you pay interest, sometimes interest is paid to you. You can also think of like sales tax as an interest, basically. You're paying a portion of the price of your item, except for you're not paying to borrow it, you're paying to keep it, right? And then that money goes to the state of Michigan or whatever state you're in. So today we're going to start with something called simple interest. And simple interest is calculated as a percentage of the original amount of money only. Okay, so for example, if you deposit $100 in an account that pays 4% interest per year, at the end of 1 year, you would have 4% of $100 in that account. Since 4% of 100 is 0.04 times 100, you'd have $4. So you would have earned $4 in simple interest, and the account would now be worth $104. In the second year, you'd earn another $4 in simple interest, making the account worth $108. So in simple interest, you only get paid on the original investment. Okay. Let me circle that here. You only get paid on this original investment, the $100. Now, if we flip to page 126, compound interest is a little different. On the other hand, it's interest that is paid not just on the original amount deposited, but on interest previously earned as well. To help you to understand the difference between simple and compound interest, let's look at two different accounts. So question 3 is going to be all about using account 1. So in account 1, it says you deposit $1,000 into an account that pays 5% simple interest. So I'll let y'all get working on this. So over here in this part of the table, it says how much interest will you earn in the first year, and then what will your account be at the end of the first year. Then you're gonna find out how much interest you are gonna earn in the second year, and then what will be in the account in the second year, and again for the third year. And I'll see what questions everybody has after number 3. So how much interest will you earn in the first year? Anybody get this one?
Yeah,
What'd you get?
for account 1,
Yep,
1,050.
would be the interest or the total?
Oh, the total, the interest would just be 50.
Okay, how did we get to 50?
1,000 times 0.05.
Okay, so $50 for the first year. And then if we add that to the original 1,000, we get 1,050.
Yeah,
Okay. Did everybody get that for first year 1?
For the second year, would you just do 1,050 times 0.05 again?
Well, that's a good question, Carter, because in simple interest, we only get interest. We only get interest on the original amount, right? Right here, we only get interest on the original amount. So compound interest, we build interest from your amount in your account. So you're right, the next year we would get interest based on this 1,050 in the account 2 down here, number 4. But in simple interest, we only get interest on the original amount. So how much interest will we get in the second year?
or you'll only get 50 again.
Yeah, we only get 50 again because it's still only based on the original 1,000, which is kind of a bummer. So we still only get this. Now, what's in our account is what was in there before, the 1,050 from year 1. So I'm adding my original 50, and then this second year's 50, I'm going to do in blue. So everybody can see that that's the new. So now I have $1,100. So how much interest do you think we earn in year 3, Carter?
Would it just be another 50?
Unfortunately, yes. This is terrible, isn't it? Because I left my extra interest in my account, but I don't get any interest on that. Okay, so I'm writing it out because it asked up here, getting an answer is nice, but make sure that you think carefully about how the amount is growing and look for patterns. So I want us to see some patterns. So there's my first year 50, there's my second year 50, and then in blue is going to be my third year 50. So now I should have $1,150 in my account. So can anybody see any patterns?
You just add 50 every year.
Yep, so we're adding 50 every year. And can you see any patterns over here in the number of 50s versus the number of years?
It's the same amount, like the third year you get 350s.
Okay. So third year, we get 350s. Second year, we get 250s. Okay, so that's something to take note of. So we're repeat adding here too, right? We're repeat addition. Just kind of making note on some things. So repeat addition, we are, let's just see, adding same amount each year. Just making some connections for ourselves here. Okay. So number 4, it says is account 2, and this works like, I think the way most of us expected to earn money, right? You deposit $1,000 into an account that pays 5%, so that's the same of the account balance at the beginning of the current year and interest each year. Okay, so we're earning interest on the balance that's in our account at the beginning of the current year. So the first year, how much interest would we earn? Oh,
50,
I'm sorry, how much?
50.
We'd earn 50? So similar to account 1 in that respect, right? Because we started with 1,000, so we're earning $50. So we'll have 1,050 in our account. Let's see if Brandon or Carter can help us with the second year.
For second year, wait, use my calculator. It's still 5%, right?
Mhm.
So it'd be 52.5. So it'd be $1,102.50 for the total.
Okay,
And then the interest would be 52.5.
okay. So that's where in second year, we're using our beginning balance or end of last year's balance. So this time we're getting interest on the whole 1,050, right? So that's where Brandon came up with 52.50. And now our balance is 1,100. $2.50. Got an extra 0 in there. So this is what Carter mentioned earlier, and almost all my students yesterday in class, they all wanted to do the same thing. They're like, they got this first table all filled out, but it was with compound interest, because that's, I think, our natural instinct, because we should be earning money on everything that's in our account, right?
Yes.
So what about the next one?
Let me type it in real quick on my calculator. The interest would be $55, or well, $52.12.
I got $55 and rounded up to 13 cents.
Oh, I didn't. Yeah, I didn't. Yeah.
So if you do 1102.50 times the 0.05, you should get $55, and then hopefully the bank rounds up like they should. 55.13.
And then for the total, I have $1,157.63.
And yep. Everybody in agreement with that? Stephen and Carter?
Yes.
Sure. Carter, you in agreement or have a question at all?
No, you got the same answer.
Okay, so we're good so far. Okay, so moving on to number 5. They're asking us just to kind of reiterate, fill in the tables. You've already found 4 of the amount. So we've already done after the second year, so we can fill that in, just the total balance that you had in your account, and then after 3 years. And then we're going to see if we can fill in 4 year, after 4 years and 5 years, what we can do to get there. So I'll let you all work on that here for a moment. I'm gonna pause it. So for a simple one, we're just adding 50 every time. And then this is filled in so far that we had for our compound. Can anybody share what they got after 4 years and 5 years?
4 years, I got 1,214.98 cents.
And it might just be the rounding that we did different.
It could be.
Did you use the whole 1157.63?
Oh, I accidentally did 12. I typed that in wrong. So it'd be off by
Yeah, I had
50, 60 cents.
Yeah, I had 1,215 and 51 cents.
Yeah, I
um,
put 1157.
Okay, Carter and Stephen agree with my 1215.
Yes.
Yep.
And then year 5. Anybody want to share that?
I got 1,276.29.
Excellent. Okay. So what do you all think here on number 6? It says, suppose you wanted to find the value of each after 20 years. Why would that be a much harder calculation for account 2 than count 1?
Because it's compound. It's constantly changing.
Okay. If I wanted to find out how much was in the account after 20 years for the simple, could I do that quickly?
Yeah,
What strategy could I do quickly?
probably do 50 times 20 and then add that to the original 1,000.
Okay,
Yeah.
because we made that connection. That's what we were doing before, right?
Mhm.
So that one would be an even 2,000. So is there a quick way for me that we know of so far? So you shouldn't necessarily know this. Is there a quick way for me to be able to jump from year 5 on a compound to year 20?
Times it by 4.
Huh?
Times it by 4.
So I could times this by 4?
Mhm.
Okay, anybody else think we could times it by
Well, I
4?
don't know, because then the numbers would change over time.
Mm-hmm. So with simple interest, we know that we're simply adding the same exact amount of interest every year. So we could just simply multiply by 20 years. But a difficulty with compound is so far, haven't we needed the last year's total to help build the next year's interest?
Mhm.
So that's where things get a little bit sticky. Okay, so let's move down here for just a minute and let's go through this solved example together. So it says, write the computation of the amount of interest in account 2 after 1 year in one single calculation. So right here, we have $1,000 plus 5% of 1,000 is my original amount plus my interest, right? Okay. Then B says, simplify the calculation using the distributive property. So the distributive property. So down below, we have 1,000 times 1 plus 0.05. The distributive property means that we're going to distribute an amount, but really we're kind of working backwards called factoring. We're gonna pull this out. So we can see that the thing that these up in A has in common is 1,000 and 1,000, right? So if we pull the 1,000 off to the side, we really have an unsaid 1 here being multiplied by the 1,000. And that 1 is similar to this 0.05 in that the 0.05 represents the percent in decimal of the 1,000 that we're keeping for interest. Let me write this so you can actually read my words. The one here represents the 100% in decimal form of the original 1,000 that we're keeping. We're always keeping that original 1,000. So if we pull out this common 1,000 out in front down here, then we're left with the 1 from our original 1,000 and the 5% of what we're gaining in interest. So now we can flip our page here and we can add the 1 and the 0.05 and say, oh, I'm really just taking my 1,000 times 1.05, and that's going to give me my amount at the end of the first year. Okay. Now part C says, what would the calculation look like for the value of the account after 2 years? So after 2 years, I'm going to have the 1,000 times the 1.05, which is the amount after the first year. And then we're going to times that again by 1.05 because that's how we find the next year's total, right? And so that will be 2 years. And notice we have 2 of these 1.05s being multiplied. This is a multiplied. Okay. Whereas back here, we were adding in simple. We're just adding 50, 50, 50, right? So number 7 says, why does the value of the compound interest account grow faster? Anybody have any thoughts?
It's because you multiply with your interest that you have added.
Okay. Compounding interest uses repeat multiplication. Whereas we said on the last page that simple interest uses repeat addition. So 8 and 9 are a little bit tricky and I'm not really sure what they're getting at. So I kind of filled in what I thought they were getting at here. So it says, let's summarize what we've learned about the growth of these 2 accounts. So account 1 is growing by exactly $50 per year, right? So the amount after any number of years looks like 1,000 plus 50 times the number of years. We came up with that on this prior page over here. Number 9 says account 2 has its value multiplied by 1.05 every year. So the amount after any number of years looks like this: 1,000 times 1.05 times 1.05, continuing the number of times the years have passed. So in each of the accounts, the value is growing, but in different ways. Fill in the blank lines in the following box. So this is going to be a really good box to kind of have a note sheet for the midterm. And to kind of think about and help you kind of keep handy there. On account 1, the simple interest account, the values grow by blank, the same constant number. So we're adding. So we want to think about the math action that we're doing. So linear is all about adding the same amount every time. So this is going to be linear. We're going to define 2 different types of growth today. One is linear. In account 2, the compound interest account, the values grow by multiplying by the same constant number. This type of growth is called exponential. So in unit 2, we're going to learn more about multiplying, which is exponential growth, and adding, which is linear growth. And then we're going to carry that over into unit 3. Any questions so far from everyone? Everybody's good? Okay. So let's go to the class portion here on page 129. It said, here's a key observation about the repeated multiplication that occurs when finding the value of account 2 in a group activity. Repeated multiplication can be expressed more concisely as using an, what is a shortcut way of writing repeated multiplication? Anybody have an idea?
Is it an exponent?
Good job. Okay. So we're going to continue with this $1,000 investment, 5% interest. And if we want to find the investment after 7 years, we're going to write it like this. So number 2 says, without using a calculator, write that expression without any exponents. Don't perform the calculation, just write it out. What would it look like? What do we have there?
Do you just write 1000 and then in parentheses 1.05 and then write that 7 times? The 1.05.
Okay, so I'm going to keep doing this. Until it looks like this. So that's what that would look like. Now, number 3 says, what is the value of the account after 7 years? So we could actually go to Desmos and put in your calculation. My kitty cat's getting out of the way. You guys see her? So
Cute.
cute. She's so cute. Okay. So if we go to Desmos, we can put in exactly what they had there, 1,000 parentheses, 1.05 parentheses, and to do an exponent, it's the shift in your 6 key, and I'm going to put 7. So did everybody get $1,407.10?
Yes.
Excellent. Let me make sure. Carter and Brandon, are you good with that one?
Yeah.
Okay, and also I'm going to circle this because this is our lesson check for this lesson. So make sure you have that ready. So it says in account 1, where the simple interest is the account value goes up by $50 each year, write a calculation that would find the value after 7 years, then find the value. So we've done this one already, so I'll let you all work on that for a moment. And then you can move on to 5, 6, and 7 and figure out how you want to add those in. They're kind of quirky. And I'll be back.
You're muted.
Thank you. I asked you a question. No wonder nobody heard me. Or no wonder nobody responded. Does anybody get question 4?
Yeah, I did 1000 plus, and then in parentheses, I did 50 times 7.
Okay. Does everybody else agree with that?
I'm gonna say yeah on that one. I believe him.
You believe it? So what do we get here for number 4?
50 times 1,000.
So we should have 7 years of $50 in interest plus 1,000, so 1,350.
Mhm.
Okay, excellent. So now if you flip the page, 5 and 6 are a little weird. But it says, let's take a stab at summarizing what we've learned about linear and exponential. So we're trying to put some system to this. Don't worry about getting this filled in perfectly for 5 and 6 because I'm not exactly confident on what words I want to go in there. So we can kind of use what's in the purple here. So it says with linear growth, the value after a certain time is calculated using the starting value. And I have the starting value adding a constant. A constant value, which would in our case be the $50, right? A certain number of periods of time. With exponential growth, the value after a certain time is calculated by using the starting value and multiplying a growth factor, right? A certain number of time periods. So it says, without trying to give away the answer to question 6 too much, part of it involves a power. What is the significance of the exponent? So the exponent tells us the number of years, right? The number of time periods. So they kind of summarize it down here in purple, but it's kind of hard to pull it out. Here is the linear, and here is the exponential. And so the simple linear is the original value plus the amount of growth per time period times the number of time periods. And then the exponential compound is the original value times 1 plus the growth rate as a percentage to the exponent of number of time periods. So number 8 says, use what you've learned about linear exponential growth to calculate the value after 20 years in each accounts we've been studying. Make sure to write out the calculation that you did. So let's take a minute and do simple. And let's take a minute and do compound. And we're trying to find the amount after 20 years. So I'll let you all work there unless everybody's already there. Let me know when you're all. Ready there.
Okay.
You're ready, Stephen is? Anybody else ready? Okay, what do we think for the simple versus the compound?
For the simple one, it's 2000.
Okay. And we actually had talked about this earlier when we were saying how easy the simple was. And how do we get to the compound?
1000, and then in parentheses 1.05 with an exponent of 20.
Okay. And so in 20 years, what do we have in our account?
2,653, and then I just rounded up to 30 cents.
I think that's what I have as well. Mhm. So does everybody see how we did that? So this is our linear model, and this is our exponential. And so up here, I'm just going to have you write down a general linear model is that y equals mx plus b. And so in our case, we had was our $50 times years, right? Plus the 1,000 original. And then an exponential model is usually modeled by y equals a times b to the x. So in our case, it would be y equals the 1,000 we started with times 1.05 is our multiplier, our growth factor to the years, x. Any questions there? So I'm gonna let you all work on 9 through 14 at your own pace. We'll answer questions. And then I wanna leave like 5-10 minutes before we get off to the last bit of questions are on actually we need about 10 minutes or so on this 136. So once you've got 9 through 14 done, then 7, 8, 9, 10, and 11 are asking you to go through and find some patterns. So if everyone could work on 9 through 14, hopefully we'll be done with this in the next 5-10 minutes. So I'll let y'all work and you can kind of let me know in the chat when you're done. So, and we'll go over all this together. Quick. So we'd start with the $500 original amount, and then we've got our interest right here for simple that is calculated by $500 times the interest rate of 0.03 times the 4 years. So it says to correctly evaluate the expression, you'll need to remember the order of operations. The order of operations says that something comes before something. What is the something? Anybody know? What comes before what?
Multiplication before addition.
Okay, so multiplication before addition. And if you're rusty on your order of operations, the problems at the beginning of the lesson, they do some practice with that and go through it. So number 11 says, evaluate the expression to find how much you'd owe. So $500 plus 500 times 0.03 times 4 means that we would get, this comes out to be 60, and we have, did everybody get $560 at the end?
Yeah.
Then 12 says, perform the following calculation, then compare your result. So here, we have to do it a little bit different, right? The order, because it says describe what you did in terms of order of operation. So here we have to do the parentheses first, right? And so inside the parentheses, we have to go by order. And so that would be the 0.03 times the 4 first, which is 0.12. And then we're going to add the 1 plus the 0.12, and we get 1.2. And then the next step would be multiplying 500 times the 1.2. Sorry, 1.12. And so we still get $560. So 13 says, the reason you got the same answer in question 11 and 12 is the blank property. And remember, we did this earlier in the lesson, and that is called the distributive property. So the distributive property is like handing out newspapers to every house. We're going to hand out newspaper we're distributing. And then the reverse of the distributive is factoring. We're pulling it out. We're pulling out the same thing from everybody out front. So 14 says, describe the property you referred to in question 13 in words, then make up an example of a calculation that uses that property. And I'm going to see if anybody has a good example. I have one just to throw out there. If you don't. And then we'll go to the other. Anybody have an example for 14? I'll share.
The only
mine.
thing I can think of is like parentheses and stuff like that.
Right, which is true. I just kind of made up a word one where I would use this distributive property. And so I said you could do it in two different ways. If I bought a $20 shirt that I have to pay 6% sales tax on, my total owed, that's nothing. My total owed is what I owe the store is $20 plus my sales tax. So 20 times my 0.06. So I totally owe $21.20. But we can also use the distributed property in reverse and say 20 times 1.06, and I hop to my final total. So when it's broken apart, it's a benefit because you get to see the two pieces, right? When it's all together, you're just jumping to the end result. So like shopping at a store, the end result quickly isn't a good thing. But if you were to use this and you're at a restaurant and you want to figure out the tip, it's probably better to figure it out in pieces, because that way you know the cost of your restaurant bill plus what is the individual amount of the tip. So if you want to leave that in cash separate, and then you could add them together to get the total amount that you owe. So does anybody else have another example that they wanted to share? Okay, let's go ahead and flip to the very back page of 138. Nope, I didn't mean that, 136. So 136. Says, identify each scenario as illustrating either linear growth, exponential growth, or neither. Show enough work to justify your answer. And if you can, find the next value on the list. Review of the colored box on page 130 will be a big help. So kind of what we did here is how we kind of put this all together. So maybe let's just write down for ourselves, what would we do if it were linear growth? What would we be looking for? They both have a pattern. We just have to figure out what the pattern is and how do we find the pattern?
So we're looking for the, I don't remember what it's called, but if it's linear, the thing that adds it up every year, the
Mhm.
same rate or
Okay.
whatever.
So if it's linear, we're adding the same amount every year. Yep, we're not worried about slope and all that stuff right now. We're just doing some basic talk. So non-math people to non-math people. So adding same amount each period. Because some of these are going by years, some are going by months, some are going by miles. And if it's exponential, how can we tell?
From multiplying the same amount.
We're multiplying by the same amount. So I always look first to see the linear one, just because it's to me, the easiest one to get started with. How would I find out if I'm adding the same amount here? What would I do strategically? Does anybody have an idea?
Subtract them from one another.
So what would I
See if
subtract?
you do 570 minus 330.
Okay, so I have to do this, then the latest one or the one below, subtracting the previous one, right? So if I take 570 and subtract 330, I get $2.40. So you could do this in Desmos. So 570 minus 330. Okay. And then I would have to do that for each of those, right? 810 subtracting 570, 1050 subtracting 810, 1290 subtracting 1050, and 1530 subtracting 1290. So Does it look like we have the same amount that we're adding?
Yes.
So one thing I want to make sure everybody notes is that we said it's linear if we're adding the same amount, but to check it, we're doing the inverse operation of adding. We're subtracting, right? We're working backwards. Okay,
Yeah.
so we're definitely going to say linear for number 7. And what would the next amount be?
$17.70.
Mhm. Okay. I could also make a table here in Desmos. And put in 330, 570, 810. Oh, look at it seems to know the pattern because I am using a consistent pattern. So that's kind of cool there, right? Okay. Now that one is definitely linear. And so we don't even need to check if it's exponential. So what would we do to check on number 8? So number 8, let's see if we had the same idea and we decided we were going to take each one and subtract the first one and see if it's linear. So 13,200 minus 12,000. So that seems to be a difference of 1,200. And then 14,520. 520 divided by 13,200. Looks like we have an issue. 15,972 minus 14,520. 17,569 minus 15,972. Yikes. Oh, and that's 569.20 cents. And then we have 19,326 and 12 minus 17,569.20. Okay. So does it look like this one's linear?
Nope.
Okay. So how can we check to see if it is exponential?
Would this time you divide them?
And why are we going to divide?
Because it's the inverse of multiplication.
Okay, so if we're trying to find out what we did, what we multiplied to get to something, we could work backwards and say, well, let's divide it and see if it's the same. So I'm going to see if I can go up here and change all of these subtractions to divisions. It doesn't let me, that drives me crazy. I have to do all this. This is divided by 13,200. Okay, oops, I don't need that one. And then I need divide. I'm gonna do this. Let's say divide. I didn't do it. Trying to get a more efficient way here to do this. Oh gosh. Oh, 1572 divided by 14,520. That divide by 15,972. And then, so it does seem to work, right? 17,569.20. Okay, so it looks like the multiplier is 1.11. And so if we were going to find out what our next value would be, what would we do?
Do the number after 5 years times 1.1.
Okay, so after 5 years, we have 19,326.12. And if our multiplier is 1.1, the new number should be 21,258.73. Okay. Okay, so I'm gonna let you all work on 9, 10, and 11 momentarily here. Again. So looking at number 9, I started adding and I put it in a table, and it definitely, at first it looked like they were adding 200, but then they added 204, and then they added 208, and then they added 212, so that wasn't working. So then I started dividing to see, and it looks like it comes out perfectly 102, 1.02. That one's going to be a rounded 1.02. Let's see the next one. Again, that's going to be a rounded 1.02 and a rounded 1.02. So we can say this one's linear. It's not quite perfect, but it's, I'm sorry, exponential with a multiplier of 1.02, but not quite perfectly. And then number 10 is kind of nice because you can kind of visually see that one a little easier, because I always check the linear first. And if you take the difference here, we can see that it's 1,500. And then it looks like it's another 1,500. And then I thought, well, I'm just going to skip to the last one and see. And that one's also 1,500. And yes, they're all 1,500, by the way. So this one is linear with 1,500. And then 11 is a little bit trickier because it looks like they're adding 2, but then you can see right away that they're adding 250, so it's not linear, right? And so, Stephen, did you put it in, you were asking about this one, did you put it in Desmos?
Yeah.
You want to share your screen? Do you have it up that we can see?
Oh, no, I got rid of it. Hold on. I can put it
Yeah.
back in now.
I was going to say if you were on different devices, it might not work, but.
Is that right?
Mhm.
Okay.
Thank you.
Wait, that's not right. What did I do there? There we go.
So
Nah.
like the first one is 1.05. And then the 1.059. So that really rounds to 1.06. You're right. And the next one is 1.9. Oh, 1.08. So it's, let's look at the next one, 52 divided by 48. And this one does not appear to be a constant multiplier. No, so it's not, it's kind of up and down.
Yeah.
So, I'm actually going to show you all something really quick. I'll share my screen here. So we've got 40, 42, 44, 50, 48. And this is kind of fun. We don't need it for a couple lessons, but whenever I can introduce something cool early on, then it makes it a little bit easier to learn. Does everybody see my Desmos screen?
Yeah.
So we have, okay. Oh, whoops. My computer doesn't know I'm in Desmos. There, I'm on the screen. Okay. So I want to see a pattern for this. So I meant to do this over here. Because this was after This is my start, right? So this is gonna be 0, and then after 1 month, 2 months, oh. Oh gosh, I keep doing this. This is 2, go up and delete that, Sarah. 1, 2. I'm all over the place. I should have just. Okay, I got myself together. So if I wanted to see if this looked linear or exponential, I could just hit on this micro magnifying glass and it gives me the graph, which is cool because we're going to use this in the rest of unit 2. We're going to do some graphing. So over here, there's a magnifying glass. Does everybody see where my mouse is? And it definitely doesn't look linear, and it does look like it's growing quicker, which is exponential growth. So I can tell it I wanted to create a line that will fit this data. So if I want to do linear, I'm going to use Y1. I'm going to say I want the Y1 data, and you're going to use not an equal, because if I use an equal, I'm telling it I want it to make a table using this exact recipe, but I'm going to use the tilde symbol, and that's using your shift and the key to the left of your 1. See what it looks like? It's called a tilde. And the tilde says, I want you to create the best line possible using this recipe. And I'm going to say M, and then I want my inputs to be X1 because I want to use my table, plus B. So just the linear, the linear model that I said earlier. And it gave us a bunch of stuff that you don't know yet, and that's okay. But if this were a perfect linear match, this R squared right here on your screen would be a perfect 1.0, but it's pretty good, 0.94. So that's pretty good, but it's not quite. And then I'm going to just make a note so everybody can see this. Above is linear modeling. Okay. And then I'm going to do a note and do below is exponential modeling. And so exponential, I'm going to say if this were a perfect exponential fit, it would be Y1 and the tilde, and then I'm going to do A times B, just like we said before, not a B0, parentheses, and then I'm going to use shift and 6 to go my exponent, and I wanted to use as my inputs X1. And we're always, for our exponential modeling all semester, we're going to check this box that says log mode, make sure that that's checked. Okay. Now, again, if this were a perfect exponential model, my R squared would be a 1, but it's not. It's a pretty good fit. So again, we want the R squared to be as close to 1 as possible, but neither of these are a perfect fit. And because the exponential is higher than the linear, the exponential is the better fit, but neither of them are perfect. So I'm going to go back to our paper, and this is just going to wrap it up. That is a big introduction to more like lesson 2.5. So don't get stressed out, but I say the earlier that I introduce you to those, the better. But you're right, it's neither on this one. Neither fits perfectly, but real life never fits perfectly. And that's what I want you to remember there. And I just gave you a little segue into the future lessons. Does anybody have any questions for me before I let you go and enjoy the rest of your day?
I'm good.
You're good? Brandon, Carter?
I don't really have much. Last night when I was practicing, I almost shot a 300, if that counts for anything cool.
It does, but your math also needs to come a good
I know.
priority.
Mhm.
Carter, are you doing okay?
Yeah, I'm also.
Okay. So I appreciate you all being here because that means you're learning and you want to do well in class. If anybody has any questions, please reach out to me. Those that are on the video, please reach out to me if you have any questions as well. And I'll see you all on Thursday morning. And just so you know, Thursday, 2.2 is going to go much quicker. So if you have questions over the review or something that you need help on, we can do those 2.2 will go a little bit quicker, so we might even start a little bit of 2.3 on Thursday, just to get a little bit of ahead for Unit 2. And I can also answer questions over the Unit 2 project if people are getting started on that. Otherwise, I'll see you on Thursday.
Have a good one.
You too.